Hello and welcome. We are going to do some example problems on quadrilaterals. Hopefully you'll feel very comfortable after seeing some of these. Alright, for starters, number one, we have a table right here. And we want to match the letter that corresponds with the proper item, the proper special quadrilateral here. This is mapped in such a way that, actually, you know what, this is kind of improper. I should have arrows drawn here. The arrows shoot out toward what you can call the quadrilateral based on what information they give you. So, in other words, the least specific quadrilateral type would be C, because everything's stemming out from C. And again, I feel bad that I didn't kind of have that before. So C must be the quadrilateral itself. Everything else from there is a special type of quadrilateral. For example, if I go to one pair of parallel sides, well, that would be a trapezoid. So trapezoid is F. Okay. A trapezoid whose non-parallel sides are congruent is called an isosceles trapezoid. Now if I start from the quadrilateral and jump out to here where I have no pairs of parallel sides, that would be a kite. Now a kite has more stuff than no pairs of parallel sides, but that's at least one thing that it does have. There's nothing else that stems from kite. It can't get more specific than that. I guess it can. You can have a kite with right angles and such, but that's besides the point. Two pairs of parallel sides, this would be a parallelogram. That is what it is by definition. And then if you have a parallelogram whose angles are right angles, then that's a rectangle. So E is your rectangle. From the parallelogram, if you make all sides congruent, you've made a rhombus. Now I'm not actually drawing these shapes for you, just kind of giving you the definitions. You can look at the shapes, or better yet, we'll probably see some in examples later. Now if you take a rhombus and make all your angles right angles, you've made a square. Or if you take your rectangle and you've made all sides congruent, then you made a square. So as you can see, sides congruent, right angles, or right angles, sides congruent, you still get to the same place from the parallelogram. So A is the square. And there you are, that's number one. Okay, number two, what happens is you're given a shape. Based on the properties, you're supposed to say what the most specific name of it is, basically the most precise name, something that, you know, it could be other things, but what is the best name you could call it? And you can only go by the properties, not by the actual image itself, even though sometimes, yes, it will kind of look like the shape that's being referred to. So right here, what you have are opposite sides that are parallel. Okay, and then, so we know it's a parallelogram, at least, but what could it more specifically be? Well, we have diagonals that are perpendicular. And in a parallelogram whose diagonals are perpendicular, that's actually one of the properties for a rhombus. This is most specifically the name I could give it. If anything more specific, I could have given it square, but I would have to have all right angles here or diagonals congruent or something like that. That's most specifically what I could give it, and for that reason. Okay, this one right here, I have one pair of opposite sides that are parallel, and because these opposite angles aren't congruent, then I know it's not a parallelogram, so it looks like this is going to be a trapezoid. We'll see if it is an isosceles trapezoid or not. So I have one pair of parallel sides, which is why I know it's a trapezoid. Alright, based on this information here, I'd like to see if it's possible. I mean, it must be possible, these are same side interior angles, but if these same side interior angles, 64 plus x equals 180, if I call this x and I call this y, I need to see if y and 64 are the same and if x and 116 are the same. Because that would mean it's an isosceles trapezoid, because in an isosceles trapezoid, base angles are congruent, which are the ones that are on the bases themselves. So yes, x is 116 and y is 64. Because base angles are congruent here and here, then this is an isosceles trapezoid. So base angles congruent makes it more specifically isosceles trapezoid. By calling it a trapezoid, I'm sure you'd get some sort of credit, maybe half credit or something like that for 0.5 of the 2 points, and you give yourself a reason, but you want to get a little bit more into that and say what specifically is it. Just like we could call all these things quadrilaterals because they all have 4 sides. Doesn't mean, oh, you should just receive partial credit, but try and get as specific as possible. There's one more in this one, number 2. This time they don't give you the drawing. They're saying, hint, why don't you sketch the drawing? Now this is quadrilateral ABCD. So what I'm going to do, and I'm just going to draw 4 lines here. AB, BC, CD. I shouldn't probably do it like that. I should probably do it a little, because it looks like those things are the same, and DA. Okay, so A, B, C, D. It doesn't really matter how you draw it, but I'm kind of trying to go by the lengths themselves and say, oh yeah, you know, that fits a little better than not. Okay, so I drew these 4 things, and I need the most specific name and the identifying characteristics. Now, what happened here was when I first drew it out there, I said, now it needs to be closer because this needs to be 5 like this was 5. So, in essence, this kind of looks like a trapezoid, and almost an isosceles trapezoid, because these opposite sides are congruent, and you might call these the non-parallel sides. Here's the problem. Do we know that these sides here are parallel? The answer is no. I don't see anything here that specifies that. If they said something like, oh, AC right here was some length, whatever that length would have to be, like 15 or whatever, and this length was also 15, okay, diagonals would be congruent, therefore it would be an isosceles trapezoid. I don't see anything that says any sides are parallel. Now, let's say all of these were 5, 5, 5, 5, and 5, and it didn't say any sides are parallel. That one is still a rhombus when all sides are congruent. Automatically, when all sides are congruent, then all sides are also parallel. It has to be. Or if this was 10 right here, then automatically opposite sides would have to be parallel if opposite sides were congruent, which is pretty interesting. But this case is not. So my question is, what do we call it? It still has a name. In this case, this is the most specific name you can give it. Don't know anything else about it, even though it looks like a trapezoid. Okay, number 3, you're going to have 4 points here. A is at 0, 4. B is at 4, 0. C is at 0, negative 4. And D is at negative 4, 0. We have to identify what kind of shape it is by filling in the blank. So I know you might be able to know what it is just by looking at it. Maybe you've done a problem like it before. You still have to find the information that they ask for you to find. There are some shortcuts to finding some of them based on what you do. I will drop these by you in case you want them, but I am going to delete them after some point because I need the room to write my answers here, because I'm not going to be using these. If I want to find the length between 2 points, I have to find the distance between them. And the distance formula can do that. But better yet, I will be using what's called Pythagorean theorem, because I'm going to be making right triangles on my graph. And slope formula is here, but also when I make right triangles on my graph, they will also be the slopes as well. So while you can look at those for a moment and even pause the video if you'd like, I will be deleting them soon because I'm going to be doing this. Going from, wait, hang on a second, let me label these. A, B, C, D. So going from D to A, I want to know how much do I rise and how much do I run. Okay? I'll be doing the same for A to B. How much do I run? How much do I guess, fall? And from B to C and from C to D. Drawing these triangles are, to me, they're always best, especially when these can be counted. It's very quantifiable. So, what you have here is from A to B, you run 4, you rise, as you run to the right, I would call this falling, so you rise negative 4. From B to C, you fall negative 4, and you run to the left, so that's going to be negative 4. C to D, you run to the left, so it's negative 4, and you're rising, so it's positive 4. And from D to A, you rise positive 4, you run positive 4. All these are right triangles as well. Okay, so as I delete these things, because now I'm not going to be using them, I'm sorry if you will be, pay close attention here. If I want to find the slope of AB, that's going to be rise, negative 4, over run, 4, which is negative 1 over 1, or just negative 1. Slope of BC is negative 4 over negative 4, which is positive 1 over 1, or just 1. Slope of, well, they don't ask for slope of these guys. Okay, well, that's all they ask for those two slopes. But these triangles were still pretty good, because what it allows me to do is it allows me to also find the distance, the lengths. The length of AB, okay, I'm just going to do this once, because we do need to know what the length is. Let's call this portion of AB C. So you're looking at a right triangle here with this and this. These are my legs. Now, if you're referring to length, I would just call this -4 positive. It won't matter anyway, because what's going to happen is I'm going to be doing Pythagorean theorem, which is a squared plus b squared equals c squared. So even if I did -4 here, I'm going to be squaring the value, and it will give me positive 16. So c squared is 32. C is the square root of 32, which is also 4 root 2. So this distance right here is 4 root 2 units long. Now, as I write this answer down, and I erase my work, sorry. As I write this answer down, the question is, do BC, CD, and DA all have the same lengths? In other words, do I have to do all that Pythagorean theorem work or distance formula to figure these out? The answer here is no, and here's why. All of these have the same exact right triangle. They are all congruent by side, angle, side. It's 4, 90 degrees, 4. Even with the -4s, keep in mind that distance is still 4 between 2 points, the absolute value of. So all these things would have the same hypotenuse. So I did the work once to figure out what that length was. All the rest are going to be 4 root 2 because they have the same right triangles. Now, there is a chance that if they have different right triangles, they could still have the same length. I still haven't thought of a one to, oh, okay, here's one. If I have a triangle, a right triangle whose legs are 7 and 24, this one will be 25. Don't take my word for it. Go ahead and try it with Pythagorean theorem. Also, if I do one here with legs 15 and 20, you'll also get 25. So it's possible to have different legs and get congruent hypotenuses, but it's not possible to have the same legs and different hypotenuses. If you have the same legs, they'll have the same hypotenuses. Hypotenuse? I'm not really sure. Okay, they have more questions down here. Since AB, and look, they actually lead you to the fact that, hey, you're going to get the same answer. Since AB, CD, BC, and DA are all congruent, ABCD at the very least must be a rhombus because all sides are congruent. Now, we did find the slopes of AB and BC. Say, since the slopes of AB and the slope of DA are opposite reciprocals, which I'm not sure why they said that because we never found the slope of DA, but we could. It looks like it'll be 4 over 4, which is 1 over 1, or 1. Since DA is 1 over 1 and AB is -1 over 1, and those are opposite reciprocals, the measure of angle DAB is going to be 90 degrees. Opposite reciprocal slopes gives you a right angle. So the question's asked kind of wrongly, but should have said BC instead of DA. Oh well. Therefore, ABCD is most precisely classified as A. So let's keep going with this. All sides congruent, at least one right angle. All of them, you might figure out at some point, have to be right angles. If all sides are congruent, opposite sides are parallel. If opposite sides are parallel, and if a line is perpendicular to one of two parallel lines, then it's also perpendicular to the other, and so on and so forth. This is a square. And that's it, and that's all. It's a pretty interesting problem. You can shorten this a whole lot by doing this instead of your other formulas. I totally recommend this for a lot of reasons. As I said, you see your triangles, you know they're the same, you can save yourself time as you go through it. Number 4, solve for the following. Variables or missing angles. All right. So, based on the information they give you, you have to first figure out what shape it is. In order to figure out what shape it is, you'll be able to know what kinds of things you can do with it. What I have are diagonals that are bisecting each other. That would make it a parallelogram. What I also have is diagonals that are perpendicular to each other. Now, there's a chance for diagonals to be perpendicular to each other and for it to still be a generic quadrilateral. But this could also be a rhombus or a square, potentially, or a kite. In this case, though, because both diagonals are being bisected, it can't be a kite. And because we don't know that these are right angles here, actually, I take that back. I know they're not right angles. I know that this is at the very least a rhombus, which means that the diagonals bisect these guys right here, so this also must be 30. That's just making sure you keep that in mind. So that means this is 60 degrees total, so this can't be a square. So this will be a rhombus, and with that, you might need to mark anything else that you feel is necessary here to figure out everything else, because there are 3 variables we need to solve for, x, y, and z. All right, so let's start getting to work here. Let's do x first, because all sides are congruent. 5x minus 16 and 2x minus 7 will be equal. Subtract 2x and add 16, you'll get 3x equals 9. Divide by 3, you'll get x equals 3. So unfortunately, it looks like these x's don't really help you find anything else, and you're not supposed to find the lengths of the missing sides. So let's just find y and z from here. If this is a right angle, all 4 of these will also be right angles. And because opposite angles are congruent, and because the diagonals bisect the angles, these have to be 30. So here I have 30, here's a right angle, and here's y. In a right triangle, your non-right angles are complementary. So instead of writing 30 plus 90 plus y equals 180, I'll just write 30 plus y equals 90. And y equals 60. And then last is z, and actually this angle is 90 degrees right here, so I could just go straight from there and say 3z minus 2 equals 90. And 3z equals 92. This isn't a great problem. Z is 92 over 3, whatever that is. I'm not going to deal with that. It's not divisible. It's 30 point. It's 30.6666, whatever. So there are those 3. So your answers again were x is 3, y is 60, and z is 92 over 3 as an exact fraction. If they ask you to round to the nearest tenth, please do so. Okay, this time they tell you what the shape is, in which case you can start marking some things down. Even though it looks like the shape, you can never know for sure unless they give markings or they tell you. So in a kite, it has 2 pairs of adjacent sides that are congruent. Boom and boom. Those sides will never be parallel, or opposite sides will never be parallel or congruent to each other. And there is a right angle within the diagonals which bisects this diagonal. Doesn't look like it'll matter here, but it does matter that these are right angles, because we have to find some variables here, and it looks like we have to solve for x minus 3. Okay, let's do x first. These 2 are equal, so we'll set them equal. Okay, subtract 2x, subtract 7, you'll get x equals 5. And like I said, you can double check your work, but they're not asking you to find the missing lengths. Just find, solve for the missing variables. And again, I'm not sure why they did. See, I don't know why that x is there. Maybe as a decoy. Say, do I set it equal to this? But again, we don't need to find the lengths of them. I probably should, but I'll be safe on time. Okay, right triangle. Oh, also, one other thing with the kite. This diagonal, sorry, here I should say this. This triangle is congruent to this triangle here, or this triangle is congruent to this triangle here, etc. By CPCTC, you could determine that this angle is bisected by the diagonal here. Something that will be important whenever I find out what this one is, and same with this one here. So I could either say this is 35, or I could find this one first and say that y is going to be the same thing. Basically, in a right triangle, once again, these angles are complementary, so y plus 35 equals 90. Therefore, y equals 55. Oh joy. So y is 55 degrees, and that's it. They don't ask for anything else. But the kite, like I said, has a lot of complex stuff in it. Just make sure you know where to go with it. Making sure there's nothing else down here. Oh, 5 and 55. A lot of 5s. Moving on. Here you have, ooh, a 1, 2, 3, 4, 5-sided shape known as a pentagon. Hey, remember those? In this here pentagon, there are 3 triangles which you can draw from its interior angles, and the interior angle sum of a triangle is 180 degrees. So for 3 triangles whose interior angle sums are 180 degrees, you should get 3 times 180 which also goes by this formula right here. 5 is the number of sides or angles, which is 540. So the interior angle sum is 540 degrees. What does that mean? Well, if I add all these guys together, I should set it equal to 540. Never lose that train of thought. All right, without calculator, here we go. 219, 362, I hate doing this, 362, 454. So x plus 454 equals 540 degrees. So x equals, what was that, 86? So x is 86 degrees right there. So again, it came about by knowing the interior angle sum of any pentagon and going the rest of the way. Okay, here I have a parallelogram. Opposite sides are parallel and congruent. It looks like congruent is going to be the only thing that matters here. So I have two equations here. I have 4x plus y equals 8, and I have 2x plus y equals 6. This is set up very well for elimination. In other words, if I multiply the whole bottom by -1, I'll get -2x minus y equals -6, and I can add down the list where I combine like terms because both sides of the equation are equal. 4x minus 2x is 2x, y minus y is 0, and 8 minus 6 is 2. So x equals 1. Substitute, I'll take this equation here and solve for y, and y equals 4. Normally I'd write it as an ordered pair, but it doesn't really look like these are like actual graph things or anything like that. Okay, solve for x. 1 and 4. Okay, solve for x, use similar triangles. Yes, these triangles are similar by the side angle side similarity property, meaning these have the same similarity ratio. What is the similarity ratio? How much is this growing by? If this was, I can't call it x, if this was y and this was y, the original side length is y of the original triangle, the next side length of the bigger triangle is 2y. So it's y over 2y. That's 1 over 2. So the similarity ratio from small to large is 1 to 2. Okay? So not sure how keen you still are in similar triangles there, but basically if I redrew both triangles so they were separate from each other, here's what I'd be looking at. I'd have this triangle here and this triangle here. Okay? Pretend like they're similar. I pretend like I just grew one from the other. So this length is x, this length is x plus 6. This length is 3x. This length is 4. Guess what? This length is 4 plus 4. And if this length was y, this length is 2y. I'm not asking you to solve for y. I'm just giving you the example of how 1 to 2 is coming about. So why does this matter? Well, the 1 to 2 similarity ratio would be equivalent to x plus 6 in the small triangle and 3x in the large triangle. Basically, 3x is twice as large as x plus 6. So to match x plus 6 with 3x, I have to double x plus 6. If you cross multiply, you'll see that. You'll get x equals 12. To double check that, 12 plus 6 is 18. 3 times 12 is 36. This should be twice as large, just like how this one grew twice as large there. And there you go. Okay, use the properties of each figure to find the missing coordinates without introducing any new variables. So what's going to happen here is you're going to look at things very generically and try and determine what it is based on the shape that's given and the coordinate points that are given. So in this case you have a rhombus, which means all sides are congruent. Now all of your vertices here are meeting at axes, right here, the y-axis and x-axis, and the diagonals are perpendicular bisectors of each other. So, because the diagonals are intersecting at the origin, I know these parts are exactly congruent, which means this is a units long and negative a units long this way. This is negative b units long this way, so this must be b units long this way. And this way is height, so S has the coordinate points 0, b, just as a rhombus is. Okay, this one's an isosceles trapezoid, and in an isosceles trapezoid, opposite sides are parallel, or opposite bases are parallel. The bases are parallel, and non-bases, those opposite sides are congruent to each other. Now there's an important facet using that kind of isosceles trapezoid, because what's true is in the middle there's a rectangle if I draw down altitudes here, and on the outsides you have a right triangle, or congruent right triangles, with the same lengths here and here. Now, this Q goes up to BC, so this length must be B, and this length must be C right here. So this length right here is C because it's a rectangle, so R's height at the very least is C. Now its length is a little shorter than A units long. If S goes all the way out here and is A units long, and as I said, these triangles are congruent. If this is B, then this is B. This is A units here, this is B units here. So this portion right here, how far is R going out from the origin? A minus B. You go A units long, you take away B units, you're going to get as far out as R goes right there, which is A minus B in the X direction and C in the Y direction. Here you have another isosceles trapezoid, and same thing with the right triangles that I was saying before, only this time they're giving you information in a different way. The vertex E at the top of the base is on the y-axis and D sticks out in the other direction. And we have to figure out what E and D are based on F and G. Let me start with F. F is going A units out here, and it's going B units up. So we know that E is also going B units up because these opposite sides are parallel, and this base is on the x-axis. So this has the same height, so coordinates of E are at 0, B. D, what we have to do is find out this length here, and as I said, it will be the same as this length here. If this is A units long here, and G is out at A plus C units long, then this must be C units long right here, which also means this is C units long right here, but it's going in the negative direction because it's on the x side of things. So the coordinates of D are negative C, 0. I think that's it. Okay, those are those problems there. Okay, so here's number 6, which I think is the last one. You're given a parallelogram. Okay, now, so for parallelogram, you will only be able to use a couple of bits of information, like its properties, and then they give you this part as well, and then you can go on and say, all right, it might be a rhombus. So, parallelogram, what do we know? Opposite sides are parallel. Okay. AE and AE is congruent to itself, which is interesting, something that we're going to be using here. It looks like that'll be reflexive property. BE and DE are congruent to each other. That's one of the properties of a parallelogram. Diagonals bisect each other. So this diagonal here bisected this one, and these two parts are congruent. Now I'm going by the proof steps, so you have to follow those. It looks like you just need to give the reasons for their statements. Angle AEB and angle DEA are congruent to each other because these are right angles. Right? It was given that these are perpendicular. All right angles are congruent. Going down, see, I have to keep going back up to the thing. That's what makes it troublesome. Therefore, AED is congruent to AEB. These two triangles here are congruent because, let's see here, we have AED, AED, and AEB. It looks like we have side, angle, side, and side, angle, side. Even though they're right angles, doesn't just mean it's HL. Oh, they already gave their reason. I'm sorry. So AB and AD are congruent. But which ones? A, B, and AD are congruent right here and here by CPCTC. So AB is congruent to CD. Boom, boom, boom. Because opposite sides of a parallelogram are congruent, and AD is congruent to BC there. So sides of parallelogram are congruent. Sorry, I'm going quickly through this. I'm short on time. Someone came in the room earlier, so I had to cut that part out. Therefore, all of these parts are congruent. AB, BC, CD, and AD. You can take a look up here and notice that I've now marked them all congruent. Okay, it's kind of transitivity, transitive property of congruence. Boom, boom, all four are congruent. Oh, there, it says it right there. And therefore, ABCD is a rhombus because all sides are congruent. And that's it. So you have to use some of the properties of the parallelogram, and obviously they gave you a lot of statements for you to work with. You go for those and you do the rest. So these two, property of parallelogram here, opposite side of parallelogram are congruent, another property. All the rest is kind of there filled out for you. Okay, so that's it. Sorry that I went a little quickly there, but I want to make sure you had some time to absorb some of it. Meanwhile, I can't really say it more than once in different ways sometimes, so I think this was the perfect way for me to go about it. Anyway, hope that was helpful. Fiend!